So there's quite a bit of material to summarize from last night. Maybe I should stand closer so you can see me. The board is filled up. The idea is that we want to quantize the electromagnetic field in a series of procedures, a series of steps. The first is to write down the equations of motion, which are Maxwell's equations. And then by a deductive procedure, we would go through a Lagrangian, which would reproduce those equations of motion, and then transform from that over to a classical Hamiltonian. Then after that, the classical Hamiltonian would be quantized to create a quantum Hamiltonian. This is a procedure for quantizing the electromagnetic field, and it's based on the procedure which would work for mechanical systems. I haven't outlined that in diagrams tonight, but it was on the board last night. Now, in any case, the actual procedure we're going to follow is to skip the Lagrangian stage. We're going to go directly from the equations of motion to the Hamiltonian. The Hamiltonian depends on Q's and P's, canonically conjugate variables in classical mechanics. And so in order to do this, to go from the equations of motion to the Hamiltonian, we will need to guess what the canonical Q's and P's are, as well as what the Hamiltonian is. And so I've outlined for here most of what we did last night in doing that. We actually carried it out mostly for the free field case only, but it outlines the procedure. So let me summarize the main results here. To begin with, the equations of motion that we start with are Maxwell's equations, but we write them in terms of potentials because we suspect that's closer to what we need for a canonical QP description of the field. And if we write the Maxwell's equations in terms of the scalar and vector potentials, working in Coulomb gauge, which fixes the non-physical part of the potential, then those equations are given right here. This is really equivalent to Maxwell's equations, assuming we have Coulomb gauge. As you see, there's a Poisson equation for the scalar potential, and there's a more complicated equation for the vector potential, which involves time derivatives. So the A equation is a dynamical equation. Now, in the first stage towards carrying out this program of constructing the classical Hamiltonian, we'll worry about quantizing after we get the classical Hamiltonian, and maybe we'll get to that at the end of the hour tonight. However, most of tonight is going to be spent on working on deriving the classical Hamiltonian and the classical Q's and P's. So with that in mind, the first thing we're going to do is to simplify it by working with the free field only, setting the rho and the j equals to 0. If we do that, then the phi equation just becomes the Poissonian, not the Poisson equation, it becomes the Laplace equation. And the unique solution of that, which vanishes at spatial infinity, is just that the phi is equal to 0. So for the free field, there is no scalar potential. That kills this other term over here, this right-hand side term in the A equation, and j is 0 also. So all that's left for the vector potential equation is just the wave equation for the vector potential itself. But we must not forget that this has to be in Coulomb gauge, so the vector field A is divergence-free. So these are the equations we want to solve. Now, the process of guessing the canonical variables, our approach to that will be to look at the solutions of there's no solution needed for the phi equation. We'll look at the solutions for the vector potential, and we'll look for variables which simplify the description of the solution of that equation as a means for guessing what the canonical variables are and also guessing what the Hamiltonian is. So the first step in that is to write down the general solution of the wave equation. Physically, of course, this means, since this is the free field, this means we're talking about light waves in a vacuum. And the simplest way to write the general solution is as a linear combination of plane light waves. And that's what's achieved here by this first formula here for A of x. A of x is given by, there's a 1/square root of the volume of the box. We switch to box normalization here. That's why the Fourier series are sums on k values running over the discrete k values in k space rather than Fourier integrals. But in any case, that's the first part of this. And the rest of this is basically just, as you can see, it's just a wave propagating in the k direction. It's a real wave because of the complex conjugate here. The multiplicative factor is a vector, which I'll call the mode vector for the wave. This is a complex vector, which is required to be transverse. I say it right here. This is a transverse condition on the complex vector. Transversality, of course, applies in k space. And we do this because that's what's required to make A itself transverse the divergence of A. In any case, because C is a transverse vector, it lies in the transverse plane in k-space and therefore has only two independent complex components. But the statement then is that a general solution for a vacuum light wave is given by this sum here, in which these C sub k's parameterize the solution. For each different k value, direction of propagation, there are actually two complex numbers, or two independent, or four real numbers, the components of the C's, the two independent components of the C's, the mode vectors, which specify the parameters of the light wave, all possible light waves with a given k value. All right, so that's what this is general solution. Now, coming from the wave equation, the C's, the time dependence of the A is contained in the time dependence of the coefficients. And that time dependence is rather simple. There's the equation of motion right here for the ck vectors. Ck dot is minus I omega ck. It's a simple equation of motion. And the solution is simple too. It just evolves by a phase factor e to the minus I omega t. Now, so this allows us then to write the time derivative of A also as a kind of a Fourier series, where now I've written minus I omega ck instead of ck dot here for the coefficients. This gives us two Fourier series for A and d A dt. A and d A dt, okay, so this is a transformation of Fourier series, general solution. So these ck vectors, these mode vectors that I'm talking about, characterize the solution, and these are variables which will be used to guess the canonical variables for the field a few steps down the line. The first step of this equation can be regarded as a coordinate transformation on the state space of the electromagnetic field. The A and d A dt specify a complete set of initial conditions for the wave equation because it's second order in time. As you can see from these formulas, if you know what the ck's are, the mode vectors, that allows you to determine A and d A dt just by summing up the series. It's also true that the knowledge of the A's and d A dt allows you to determine the C's, and that was worked out in the last lecture, which I won't repeat the details of it, but here's the formula, is that the mode vectors ck are given in terms of the Fourier amplitudes of the vector potential A. This is an arrow here meaning a vector, and the time derivative of the vector potential, here's the expression for it. So this is an invertible transformation and takes us from one description of the state of the field to another, which is these mode vectors. Now the mode vectors are transverse because that's a transversality condition. So therefore we can expand them as linear combinations with scalar coefficients, still complex, but scalar, of unit vectors, which we choose to be orthonormal, which span the perpendicular plane in k-space. We call these polarization vectors and denote them as epsilon k mu. K itself gives you the direction of k and therefore the perpendicular plane, and the mu runs from 1 to 2, which, as you see here from the sum, which gives you the pair of polarization vectors that span the perpendicular plane. And so this then gives us these ck mu scalar coefficients. The combination of k and mu is a frequent occurrence in this theory, and it can be thought of as representing what we call a mode of the electromagnetic field. It consists of a direction and a magnitude of here's a k vector, direction of propagation, and magnitude energy as well, of the wave, as well as a polarization of which there are two choices. There's two choices of polarization for a given direction. This is how light waves work. So we call this a mode index, and it's convenient to abbreviate it with a single symbol lambda. It saves a lot of writing if we do that. In any case, when I refer to the modes of the electromagnetic field, this is what I'll mean, a combination k mu, which also will be noted by lambda. So so expanding the mode vectors ck and linear combinations of the polarization vectors allows us to rewrite these Fourier series in the form you see is in the middle term here. It's really just the same as before, but now there's a sum on k and mu here, and we have ck mu and the polarization vectors, otherwise it's the same series. And then by just using this notation, replacing k mu by lambda, I have yet a 1, 2, 3, a third version of the Fourier series where we're now summing over modes. Here, these C lambdas are the complex mode amplitudes. There's one of them for each mode, or equivalently two of them for each k value in k space. And this, is, once again, is a general solution of the free field wave equation. So in terms of coordinate transformations in the state space, we can go from the mode vectors, the CK vectors, over to the C lambdas, the collection of scalar mode amplitudes, and that takes us to yet another complete and minimal description of the state of the field, because it's invertible transformations going back and forth. Now, looking at the time evolution of the mode amplitudes, they've evolved. The simple equation of evolution is right over here. It's the same. It's really the same as the vector. We just projected out the components along the polarization vectors. So the solution is that the initial value just gets multiplied by a phase factor, e to the minus I omega t. So in the complex plane, the mode amplitudes, the C lambdas, evolve by evolving on a circle in the complex plane in the clockwise direction by angle omega t, as you see from this diagram here. And at the end of the hour, I was pointing out that this reminds us, I hope it reminds you, that of the harmonic oscillator, the one-dimensional harmonic oscillator we dealt with last fall, which also gives rise to a circular motion in the complex plane in which the real and imaginary parts are the position and momentum of the oscillator. It may be necessary to scale the Q and the P to make that happen, but you can make it happen so they turn into circular orbits. And so that's a picture we have from harmonic oscillators, and it suggests that the evolution of the mode amplitudes is described by a harmonic oscillator. This would be one harmonic oscillator for each mode with a frequency omega, which is determined by the dispersion relation for light waves. And if that's true, then the suggestion is that the Q and the P for the given mode are proportional to the real and imaginary parts of the C's, the complex mode amplitudes. And so we'll guess that these C's are some proportional factor we'll call K, the proportionality coefficient, times what I'll call Q lambda plus I P lambda, which are the Q's and the P's of the electromagnetic field. And if we do this in the Hamiltonian, it's just a sum of a one-dimensional harmonic oscillator, one for each mode of the field, summed over all the modes, and it's the frequency divided by 2 times Q squared plus P squared. Frequency, by the way, put a lambda subscript on it because lambda contains both K and mu, and the frequency is a function of K. It's C times K. So again, it's a dispersion relation for the light wave. So this is just to emphasize that omega depends on lambda. If I didn't put that in there, you might think I could take it out of the sum, which I can't. I actually can't do. And I think that takes us up to the end of the hour last time. And so now the problem is, so I hope that's clear what we're doing. And so now the problem is to complete these guesses and see that they work and fill in just a few details. But notice that altogether now we've got coordinate transformations on the state space of the system taking us from A and dA dt all the way to the Q's and the P's of the field, a collection of Q's and the P's to describe the dynamical state of the system. All right, so one of the problems obviously is going to be to determine what the constant K is. And here's our approach to this. We are going to guess, based on mechanical systems, that the Hamiltonian for the system is actually the same as the energy of the system. So the energy of the system, and I'll say again, we're dealing with the free field now. We're ignoring any matter, so it's the energy of vacuum light waves. The energy of the system, according to electromagnetic theory, I'll write H for it because it's going to turn into the Hamiltonian, but it's just the energy of the system. It's the integral over space, d cubed x, of the electric field squared, E squared plus B, electric and magnetic field squared divided by 8 pi. Like this. This is what it is in Gaussian units. If you prefer SI units and want to put in ugly epsilon naughts and mu naughts in here, you're free to do that. This is obviously more symmetrical. All right, now this integral is only going to be taken over the box. We'll eventually let the volume of the box go to infinity, so this will turn into the energy in the field everywhere in space. And so now we'd like to identify this H with that Hamiltonian down there, the harmonic oscillator Hamiltonian. Can we do that? Well, we need the electric and magnetic fields, obviously. And those are given by these at least indirectly, by these Fourier series for A and dA dt. Since we're dealing with a free field, the scalar potential is 0. That means that the longitudinal component of the electric field is also 0. And that means the electric field is purely transverse. You know that about light waves. If the K is going in one direction, E and B are perpendicular to it, so you can see that E is transverse, and so is B. That's true for a light wave. If you have static electric fields around, that's not true anymore. Anyway, for light waves, E is purely transverse. So that means the electric field E, which I'll write as E of X, which is the same thing as E transverse of x are the same for the free field, is minus 1 over c dA dt, like this. And the dA dt series is given right over here in various forms. I can write it out like this one here. It's going to be minus 1 over c, 1 over the square root of volume v. We have the sum over modes lambda. We have minus I omega mode amplitude c lambda, polarization vector epsilon hat lambda e to the I k dot x plus complex conjugate. I'm mainly just copying the dA dt series and just multiplying by minus 1 over c. Anyway, that's the electric field. As far as the magnetic field is concerned, this is, of course, the same thing as del cross A. And if we take the series for the magnetic field here, here's the latest version of it on the right. When we take the curl of it, del cross is going to bring down an IK cross from this phase factor exponent. So this is going to give us, I'll bring it over here, it's going to be 1 over the square root of volume, sum on the modes lambda, and then we're going to have I times c sub lambda times k crossed into epsilon hat lambda times e to the I k dot x plus complex conjugate. That's the magnetic field contribution like this, written in terms of the mode amplitudes, the c lambdas. All right. Now, this integral has got obviously electric and magnetic terms. Let's look at the e squared term alone. This is, of course, 1 over 8 pi times the integral over space of just e squared. And then for e squared, allow me to plug in the square of this Fourier series here. For that, I'm going to need 2 copies of the Fourier series. There's also the prefactors get squared, so let me take the e squared out here. Squaring the prefactors, we get 1 over c squared, 1 over the volume v. By the way, I'm sorry, the speed of light I'm trying to write as a lowercase c, and the mode amplitudes is a capital C. I hope there won't be confusion about that. But in any case, we get this for the prefactors, and then there's going to be a double sum on k and mu and k prime and mu prime. That's the same thing as the lambda prime sum we get here. There's going to be one factor of e here, which I'll write this way as minus I omega c lambda. No, let me write it as c sub k mu. Polarization vector epsilon hat k mu e to the I k dot x to the I k vector dot x vector, like this, x vector plus complex conjugate. And then that needs to be dotted into a second e vector, which I'll write this way as complex conjugate plus I omega times c sub k mu times epsilon hat k mu times e to the, this should be starred because it's the second term, e to the minus I k dot x, like that. And I actually need to prime the k and the mu of the second term because it's a different index of summation. I need to prime the k's and the omegas as well, like this, okay? So this is what you get by the e squared term, which is, let me separate off some of this stuff, which is the e squared term, which is just one of the 2 terms of the energy for the field. Now, multiplying out this e squared, there's obviously altogether 4 terms. If I look at the first term and the first e and the second term and the second e, I'll call that a cross term. Let's just look at that cross term. So we'll take one cross term, we'll call it one x term as a cross term. What's that equal to? It is 1 over 8 pi integral d cubed x over the volume of the box, 1 over c squared times the volume of the box downstairs, and sum on k mu and k prime mu prime. So this is a calculation we need to go through here, and I'm working through it. So the product of these 2 terms, I times minus I, is 1. We have the 2 frequencies, omega, omega prime. We have the c values. We have c sub k mu times c sub k prime mu prime complex conjugate. We have the polarization vectors epsilon hat k mu dotted into epsilon hat k prime mu prime complex conjugate from up here. And then we have the phase factors, which is e to the I k minus k prime dotted into x. right? So that's one cross term, the one that I just drew up here with the arrows. Now, this can be boiled down quite a bit. The integral over the box and the 1 over the volume V, which is that factor there, and the phase factor, which is over here on the right, doing that integral gives us a Kronecker delta because of the orthonormality of the plane waves in the box. So those three factors are going to combine together to give me a Kronecker delta in K and K prime. That in turn, it means that I can do the K prime sum, which you see here, if I just replace all K primes by K, and if K prime is equal to K, this implies that omega prime is equal to omega because the omega is just the proportional to the magnitude of K. And so after that simplification, what I get is 1 over 8 pi c squared in the denominator here. And then we get the sum on K and mu prime of omega squared, omega prime turned into omega squared. We have c sub k mu times c sub k mu prime complex conjugate. Now the two k's are the same. And we have the polarization vectors epsilon k mu dotted into epsilon k mu prime complex conjugate, and that's all there is at this stage. That's after doing the spatial integration of the box. Now the next step is that these polarization vectors both have the same k values, so they refer to polarization vectors in one and the same transverse plane. So the mu prime indices here implies by orthonormality that this is just a Kronecker delta mu prime. Because our setup of polarization vectors, they should be orthonormal in the transverse plane. And so replacing this by the Kronecker delta mu prime, it means we can do the mu prime sum, replacing all mu primes by mu, and now you see the indices in the C and C star are the same. And so the result is this turns into 1 over 8 pi c squared times the sum now just over modes, which of course is the same thing as k mu sum, of omega squared times the absolute value of c sub lambda squared. And so as I say, this is one cross term in the computation of the electric field, and this is what we get for it, and express it in terms of the mode amplitudes. All right, mode amplitudes well, I'll come back to that in just a moment. Now, there are 4 terms here for the electric field term, and there's 4 more for the magnetic field term. It turns out that this one cross term that I computed is actually equal to the other cross term, the complex conjugate here times that one, as you can easily verify for yourself. So that doubles this result. Also, the magnetic field has 2 direct terms and 2 cross terms, and you'll find if you do that the two cross terms for the magnetic field agree with the 2 for the electric field, and it doubles it again, multiplies this result by 4. Now you'll find that the direct terms in the electric field, the first term here with the complex conjugate there, and the second and the second, do not vanish on doing the integral. But if you combine them with the analogous term for the magnetic field, you find they all add up to 0. So those terms all go away. And so the answer is, the final answer we want is that the total energy, or Hamiltonian for the electric field, is just 4 times this term that I wrote down over here. So let me write it down. Here, let's do this. So the Hamiltonian, therefore, is equal to 1 over 2 pi c squared, sum over modes lambda, omega lambda squared, times absolute value of the mode amplitude c lambda squared. Well, c lambda squared, on the other hand, we're making the guess that this is k times q lambda plus I p lambda. So this turns into k squared times q lambda squared plus p lambda squared. And we see that except for constants, it actually does turn into, as we suspected, the sum of harmonic oscillators. And in fact, by comparing the coefficients of the harmonic oscillators, here we want this to be omega over 2 in order to get the right equation to motion. You can determine the value of k. And if you do this, what you find is that k is equal to the square root of pi c squared divided by omega sub lambda. And that in turn, that allows us to get rid of the k. Let me go over here and put down what that means. it means that this guess here, the c lambda k, I can now write this as putting in the square root of pi c squared over omega lambda. This is actually equal to the c lambdas, like that. We box that because there you are. This fills in explicitly the last step of the coordinate transformation. We've got the q's and the p's for the field. Then we have the Hamiltonian. The Hamiltonian does indeed turn into the harmonic oscillators. Okay, so that sets up then this series of guesses and reasonable assumptions that lead to derivation of the canonical variables for the classical electromagnetic field. There's one for each mode of the field, each k and mu value of the field. By the way, there was one student who wrote me an email with a question, and he was concerned by the fact that I made some claim that knowledge of the c lambdas was equivalent to knowledge of everything going in both directions, in particular allow you to determine the field. But he said, don't the c lambdas depend on the choice of polarization vectors? And that's certainly true, they do, because you're decomposing this transverse mode vector as a linear combination of polarization vectors. But the choice of polarization vectors is arbitrary. You can make that any choice you want. And if you do, you get different c lambdas, but they're always related in such a way that the mode vectors, the c sub k's, are always the same. So it doesn't really introduce any non-physical element in the theory. There's an arbitrary choice of polarization vectors in the perpendicular plane. Actually, simple examples of this you know already, because in optics, you're no doubt familiar with the choices you can make. You can make choices of x and y for linear polarization vectors, or x plus or minus iy for circular polarization, and either one of them work for describing the field. All right, anyway, allow me now to erase this board here because the main conclusions over here for the establishment of the Hamiltonian, the canonical variables for the field, for the free field anyway, has been established. There is a point that needs to be made, which is that the procedure I'm going through here was intended to make it quick and easy, but it involves some guesses, so you really ought to go back and check and make sure that it's all right. That would imply working out the equations of motion from this Hamiltonian, applying them to the q's and the p's, and then backtracking it through these coordinate transformations to see that it ends up implying Maxwell's equations for the a and the dA dt. That's actually quite simple, because if we do this, the equations of motion from this Hamiltonian would be, by Hamilton's equations, a q lambda dot is a dH dq lambda, and that's the same thing as omega times p lambda, and then the p lambda dot, and the omega depends on the mode lambda, the p lambda dot is minus dH dq lambda, and so that gives me minus omega sub lambda times q sub lambda. And it's easy to put these two together to find an equation of evolution for the mode amplitude c lambda. You got c lambda dot turns out to be minus I omega c lambda. Of course, the c lambdas are complex, but just by the chain you work that out, and you get this, which is the correct equation of motion for the mode amplitudes. It implies the correct equation of motion for the mode vectors, these c lambda vectors, which in turn gives you the right equations of motion for A. The combination A and dA dt give you altogether the wave equation for, it's actually this wave equation, the right-hand side is 0 to represent Maxwell's equations in the vacuum. So it works. And we end up with one harmonic oscillator for each mode with explicit expressions for the Hamiltonian and the canonical coordinates. Okay, now the next stage in this procedure is to worry about what happens when there's matter around. And so for that purpose, I need to go back to the general equations here. We're still in Coulomb gauge, but the rho and the j are now not assumed to be 0. So this means there's going to be matter. So the first thing to do is to adopt a model for the matter, and allow me to do that over here. Let's do it this way. Let's say the matter consists of a collection of non-relativistic particles. Actually, at this point, they could even be relativistic. But anyway, let's let the particles have masses. So this is for the particles now. the matter will consist of particles. They've got masses m sub alpha, where alpha runs from 1 up to the number of particles. Let's let the charges of the particles be q sub alpha, same range. Let's let the positions of the particles be r vectors of alpha, and let's let the velocities of the particles be v vectors of alpha. Let's use this notation then for describing the particles. If we do this, then the charge density, the rho, which is a function of x and t, is equal to a sum over the particles alpha times the charges q alpha times the direct delta function of x minus r alpha, which is a function of time, like this. There's the expression for the charge density. Notice the notation. The r alphas, as I just explained, are the positions of the particles. The x here is the field point at which the charge density is measured. And what this formula says is the charge density is 0 unless you're on top of one of the particles, in which case you get an infinity like a delta function weighted by the charge q alpha of the particle in question. Notice also that charge density acquires its time dependence by virtue of the fact that the particles are moving around, which is the r alpha, is a function of time. Likewise, if you want to write down the current, the current density J of x and t for a collection of charged particles like this is the sum over the particles, the charges q alpha. Now we need to multiply by the velocities, which are also functions of time, and again, a three-dimensional direct delta function, x minus r alpha of t, like this, like so, and that gives us the current density. And this all comes from some analysis of E&M, understanding what charge and current densities mean. But you can check that by this definition of charge and current density, that the continuity equation is satisfied, which I'll leave as an exercise for you. It's easy enough to do, which is important because Maxwell's equations don't possess a solution unless the charge and current density satisfy the continuity of the equation. All right, so this then describes the matter. And so we want to then plug that into the Maxwell's equations in the form that we see here for the rho and the j. Now let's take the phi equation first of all. So the phi equation is going to be, it's the Poisson equation, del squared phi is equal to minus 4 pi rho, like this. And as I pointed out in the last lecture, the unique solution of this, it has the right behavior in infinity, namely it goes to 0 to infinity. It's just given by Coulomb's law that phi of x and t is equal to the integral over the source, d cubed x prime of rho, evaluated x prime in t, divided by the Coulomb denominator x minus x prime. This is just non-retarded, it's non-retarded Coulomb's law, and it gives us a non-retarded scalar potential. If, however, the charge density rho is determined by a collection of particles like this, and you can plug this expression in, I think you need to put a prime on the x, and you can do the integrals because of the delta functions. And this turns into then the sum on alpha, the sum of the particles of the charges q alpha divided by the Coulomb denominator, which is now x minus r alpha of t. And what you see is that this does indeed give you the electrostatic potential for a collection of charges in the electrostatic approximation. It's just determined by the instantaneous non-retarded Coulomb's law for the summed over the particles. Just what you'd expect, just what you'd want. But in any case, what that means is that the Poisson equation is therefore satisfied, or is taken care of anyway, for the case of the matter interacting with the field. Now, so let's turn our attention then to the vector potential equation, which is, after all, a vector equation. What we'll do with this equation is we'll break it into its longitudinal and transverse parts. We'll do the transverse part first because in Coulomb gauge, the vector potential is purely transverse, so the left-hand side is purely transverse. The current J has both a longitudinal and transverse component, but the gradient of phi, being the gradient of a scalar, is purely longitudinal. So if we project out the transverse part of the wave equation, this is now a wave equation, you see, which is driven by a right-hand side. It's a driven wave equation. If we project out the transverse part, what it gives us is that it gives us that del squared A minus 1 over c squared, b squared a dt squared is equal to minus 4 pi over c times the transverse part of the current. So that's the transverse projection of that equation. If we take the longitudinal projection, the entire left-hand side is 0, and the right-hand side becomes minus 4 pi over c times j longitudinal plus 1 over c ddt of the gradient of phi, which is also purely longitudinal. So these are the two equations then that come out of the vector potential part of the Maxwell's equations written in terms of the potential working in Coulomb gauge. The second equation, let's get rid of or dispense with that first. The second equation is actually just a combination of the Poisson equation, which is over there on the board, connecting rho and phi, and the continuity equation. Let's just say that this stuff here being equal to 0 comes from a combination of d rho dt plus del dot j is equal to 0, continuity equation, and del squared phi equals minus 4 pi rho. By a simple analysis that I won't repeat here, it's in the notes if you want to see the details. But I'll just point out that if you take the divergence of j, which of course appears in the continuity equation, if you break j into its longitudinal and transverse parts, the divergence of the transverse part is 0 because that's the property of transverse vector fields. So I might as well replace j here by its longitudinal component. It won't change the continuity equation. And what you see then is the continuity equation is connecting the time derivative of the charge density with the longitudinal part of j. That's just what appears here. And so this is just a way of motivating, how making it plausible that these two equations combined together give you the longitudinal part of our wave equation. In any case, if you're willing to accept that, then I can just get rid of the longitudinal part because we won't need it anymore. It's dependent on the other stuff that we've dealt with already. And we're left with the wave equation here for the vector potential. And so what we can say at this point is that in comparison to the free field, when we have matter around, there's two changes. One of them is that the Poisson equation has a non-trivial right-hand side, charge density, and the solution can be written out explicitly in terms of the coordinates of the particles, as you see here, giving us phi. This is a way of saying that in Coulomb gauge, the scalar potential is not an independent dynamical variable, but rather it's a function of the particle degrees of freedom. As you see, these R alphas, that's what they are. On the other hand, the wave equation, which had 0 on the right-hand side for the free field, now has the transverse components of the current. And so this is going to represent represents the coupling between the field and the matter. It's through this equation that energy is transferred from the field to the matter, or vice versa, something we call the emission and absorption of radiation, and it's all tied up with this equation. All right. Now, so that's kind of the setup for it. Now we need to decide now how this formalism here on these coordinate transformations we went through, getting q's and p's, are going to change now that the wave equation is driven on the right-hand side by the matter, that j transverse, which is over there. And this may be a little bit difficult to understand at first, but it's based on what's called Lagrange's method of the variation of parameters. It's a way of solving driven differential equations that goes way back in history, actually to the 18th century. And it's most useful in the case of linear systems, linear-driven differential equations, which is, of course, what this is. But basically, the idea is that when you have a linear equation which has a driving term, the general strategy, you probably covered something like this in the mechanics course. The general strategy is to first solve it in which the driving term is 0. Then you have a certain description of the solution, your constants of motion or convenient variables. And then what you do is you look at how those constants of motion, they're no longer constant when you're driving things on the right-hand side, you look how they evolve. So you switch emphasis from the time evolution of the original fields over to the constants of motion or variables describing the free field solution. In any case, that's the basic philosophy. And the way it works out in the present case is this, is that we will use exactly these same coordinate transformations on the state space of the field to transform the equations of motion from the original ones over to ultimately the q's and the p's. That means that, so it's like, you see, it's like we're going to use the same definitions for these intermediate variables. You know, if you have a harmonic oscillator with a Q and a P, and it's, first of all, not driven, the Q and the P have a definite physical meaning, position, and momentum of the particle. Now, if you suddenly put a driving term in the right-hand side, you're going to change the equations of motion of the Q and P, but you're not going to change the physical definition of them. And that's just what we're going to do. We're going to leave the definitions of these intermediate variables the same. So what that means is that all these Fourier series that you see here, we're going to adopt them, take them over without modification to the interacting field. What won't be the same is the equations of motion here. These will change. These will end up having, they won't be so simple. They'll be driving terms. These are linear equations as you see, but they'll have driving terms based on the current as the way they'll turn out. They'll still be transverse. All right. Anyway, so we want to apply all of this stuff in to the interacting field. So the way we do this, first of all, is to take the wave equation and Fourier transform it, going over to k-space. The operator del squared goes into minus k squared in k-space, so this turns into minus k squared times a sub k, the Fourier coefficient in k-space. The second term becomes minus 1 over c squared times a sub k double dot, the second time derivative of the transform of the vector potential. And on the right-hand side, we get minus 4 pi over c j perp sub k, meaning the component in k-space of the current, of the transverse part of the current. I'll clean this up by changing signs, and I'll multiply through by c squared. If I use c, omega equals ck, this turns into omega squared. Let me put the a double dot term first. We have a sub k double dot plus omega squared a sub k that is equal to 4 pi c times j sub perp k. And this is having gone over to k-space, this is completely equivalent to the wave equation that we have now. Now what we'd like to do is to find out what are the modifications in the equations of motion for the mode amplitudes. How do those change? Here it's a rather simple equation. It's c lambda dots minus I omega c lambda. The way to do that is to actually just compute c sub k. Let's do the mode vectors. Let's compute c sub k dot plus I omega c sub k for the interacting field. For the free field, this would give us an answer of 0. But let's compute it for the interacting field. Here is the coordinate transformation, right here, this little box here, taking us from the Fourier components of a and a dot over to the c sub k. So let's just plug that in and do the calculation. This becomes equal to c sub k dot, there's a 1/2. I differentiate both sides of this with respect to time. I get a sub k dot for the first term, and I get plus I over omega a sub k double dot for the second term. And then I then get plus I omega over c, I omega, there's an I omega here. I get I omega over 2. I'll write down the half, and I'll bring the I omega inside, multiplying times c sub k. Here it is. We get an I omega a sub k. Then we get this times I omega gives me minus a sub k dot. Dot like that. We add these up, and you see the first derivative terms cancel, and the rest of it gives us an a double dot and an ak. If I factor out the I over omega, the whole thing turns into I over 2 omega, and then we have a sub k double dot plus omega squared a sub k, like that, which is what we have on the, it's what we have coming from the wave equation. This is then equal to I over 2 omega times the right-hand side, which gives us 2 pi I c over omega times j perp sub k, like so. And so if I were to find a place to summarize this calculation, we now have a modified equation of motion. Maybe I'll put it over here where the old equations of motion were. The modified equation of motion would be this. it would be C sub k vector dot plus I omega C sub k is equal to 2 pi I C divided by omega times J perp sub k. Let me box this off so it will be clearer. And if we project out along the polarization vectors, this turns into C lambda dot plus I omega C lambda is equal to 2 pi I C divided by omega times J perp lambda. We write it like that. J perp lambda means the component of this vector along the polarization vector with an index of mu. And so these then are the equations of motion for the mode vectors and mode amplitudes in the interacting field. It's the same left-hand side as before, but there's a driving term. And this is really just what you'd expect, as the mode amplitudes now change in time, not only in their direction as a complex number, but also the magnitude possibly, because of the transfer of energy back and forth between the field and the matter. All right, so this gives us then the equations of motion after carrying out this sequence of coordinate transformations now in the interacting field. Now, the next question then is, and in particular, it's going to give us Q's and P's, or at least guesses for Q's and P's. We're really borrowing them from the free field definition. All right, so now the next question is, what is the Hamiltonian? Let's turn attention to that. We've got the equations of motion. What about the Hamiltonian? We've got the equations of motion and the Q's and the P's. Now, what about the Hamiltonian? All right, let's see here. So I need some space. I can take this out. I can take this out like this. So we guessed earlier that the Hamiltonian should be the energy, in the free field we guessed that the Hamiltonian should be the energy of the field, which, since it was only a field, the energy was the integral of the energy density, E squared plus B squared over 8 pi. Now, however, we have matter around, so there's matter contributions to the energy, and the question is, what is the right expression for the energy, which we will interpret as a Hamiltonian, so I'll write H for it. What is it? Well, for the field part, it's the same as before. It's going to be the integral over space, d cubed x, E squared plus B squared over 8 pi. That didn't change. But for the matter part, let's put in the kinetic energy of the matter, sum on alpha of 1/2 mv alpha squared, like this, okay? So add the kinetic energy of the matter plus the energy of the field. Now, if you're trying to guess the energy for the combined system of the matter plus the field, it's not obvious that this is the answer. You might be asking yourself, where is the potential energy? We've got the kinetic energy, all right, where's the potential energy? And the answer is, we'll see in a minute, that it's actually hiding in the longitudinal part of the electric field energy. We'll get to that in a minute. But if you had doubts whether this was the right expression for the energy, there's several things you could do. One of them is to compute its time derivative. If it really is the total energy of the field, not of the field, total energy of the field plus the matter system, then its time derivative should be equal to 0. Well, you can compute that. What you do is you just use the chain rule to compute dH dt. The electric and magnetic fields depend on time, and the velocities of the particles depend on time. Use the chain rule. This all work out in terms of an E dot and a B dot and a V dot, which is an acceleration, right? And so you get expressions for that. And then what do you use for E dot and B dot? Well, for E dot and B dot, you use Maxwell's equations, which give the E and the B dot in terms of the currents and charges. And what about the acceleration of the particles? Well, that should be the mass times the acceleration. This is using non-relativistic mechanics, is equal to the charge Q alpha times the electric field divided, the electric field evaluated at R alpha, plus the velocity V alpha over C crossed in the magnetic field evaluated at R alpha. And I'm running out of space here, so I don't think I need this anymore. I don't need this anymore either. So these are the Newton-Lorentz equations of motion for a charged particle in a given electric and magnetic field. So you can plug them in here, doing the chain rule, and go through the algebra, and if you do, you'll find this is equal to 0. So that, of course, doesn't prove that it's the energy, but it proves that it's conserved. And that's a good sign that this is probably the correct expression for the energy. If you want to be more sophisticated than that, then the right way to do it is to go back to a Lagrangian now for the entire electromagnetic field plus the matter, and to use Noether's theorem, which allows you to get, it's a systematic way of getting conserved quantities, and in particular can get you the quantity that's conserved consistent with the translations in time. This is normally the definition at a more fundamental level, the definition of what the energy of the system is, and if you do that, it'll turn into exactly this expression. Yet another way to describe the whole process is to refer to the stress-energy tensor, which contains as one of its components the energy density of the field. Actually, the stress-energy tensor for this application ought to include the matter as well as the field. And if you do this, then you get the total energy density. You can integrate that over space and you get the energy. So there's systematic and more sophisticated ways of finding out what the energy is, but all of them lead to the same thing, which is that this actually is the correct expression for the energy in this model in which the matter is non-relativistic, interacting with the electromagnetic field. So, if you grant me that, then we just need to work on this Hamiltonian and to put it into a convenient form. In particular, we'd like to see it as a function of the Q's and the P's, the canonically conjugate variables for the classical system, which now must include the matter degrees of freedom as well as the field. So how do we do that? Well, let's work on the field part first. One of the differences between the free field and the interacting field, which is what this is that the electric field has both a longitudinal and transverse part. The longitudinal part and the transverse part are precisely the same thing as minus the gradient of phi minus 1 over CBA T. And I can take this out now, I think. And if we plug this in here, so if we do now the integral over space d cubed x of E longitudinal plus E transverse, that vector squared, you can see you're going to get cross terms that involve E longitudinal dotted into E transverse. This is integrated over space. We get such cross terms. But these cross terms vanish because by the Parseval identity, this can be switched over to K-space, and in K-space, the longitudinal and transverse fields are orthogonal to each other, so this integral is 0. And so this integral of the electric field energy turns into just a sum of the longitudinal part, turns into the integral d cubed x of E longitudinal squared plus E transverse squared, like so. The magnetic field is always transverse because it's a curl of A, and a curl is a K cross something, always makes it transverse. So that's the same in both the free field as well as the interacting field. Now what this means is that as far as the field energy is concerned, if we take just the transverse part of the electric field plus the magnetic field, then what we've got is the same combination of transverse electric field and magnetic field that we had in the free particle case. And if we go through exactly the same coordinate transformations, we're going to end up with exactly the same Hamiltonian, namely this one right here. It's these harmonic oscillators. So the result is that the integral over space d cubed x of E transverse squared plus B squared over 8 pi turns into a sum over modes lambda, omega lambda over 2, again, harmonic oscillators, Q lambda squared plus Q lambda squared, like this. Okay, so that takes care of the transverse part of that E. What about the longitudinal part? Let's look at that. I'll come back to the kinetic energy of the particles in a minute. Let's look at the longitudinal kinetic energy. Excuse me, the longitudinal electric field energy. E longitudinal squared. D cubed x E longitudinal squared over 8 pi. Let's put the 8 pi out front. Let's look at that. Well, E longitudinal squared is, of course, the same thing as the gradient of phi squared. And this can be written by vector identities as the divergence of phi times grad phi minus phi times del squared phi. This is really a kind of an integration by parts. As far as the divergence term is concerned, we are assuming that all fields die off at infinity. So by applying Gauss's law, this volume integral can be transformed into a surface integral which goes to 0. And so this first term goes out. What's left over is minus phi del squared phi. However, the Poisson equation is one of the equations of motion, so del squared phi is minus 4 pi rho. And so the two minus signs cancel. There's a 4 pi and an 8 pi here. The result is that the longitudinal field energy turns into 1/2 the integral over space d cubed x of phi of x times rho of x. 1/2 phi rho. A formula you may have seen in courses in electromagnetism. It's an electrostatic formula. Except this isn't electrostatics. It's still the same result, though. All right, anyway, we happen to know what phi is and rho is, however, for the charged particles. I've erased the formulas, but we can put them back in again. Here's what they are. It's integral over space d cubed x. And for the for the potential phi, this is a non-retarded Coulomb potential, so it's a sum on alpha, q alpha divided by x minus r alpha, the magnitude of x minus r alpha, like that. That's the phi. And then the rho is sum on beta of q beta times the Dirac delta function of x minus r beta, like this. And you can see now that the integral can be done because of the delta functions. And what this gives us is 1/2 the sum on alpha and beta of the charged products, charges q alpha times q beta, divided by a Coulomb denominator r alpha minus r beta. And so look at that, there you are. This is the electrostatic, non-retarded electrostatic energy, potential energy of interaction between the charged particles, which a minute ago we were wondering where it was. Anyway, here it is. It's in the longitudinal electric field energy. It's non-retarded in Coulomb gauge. It's the usual thing that we put into Hamiltonians when dealing with particles in a non-relativistic treatment. All right? And so then the last term is the kinetic energy of the particles, which I'll come back to in a minute. But I want to make some comments about this potential energy first. We're almost there in assembling the Hamiltonian or the total energy of the matter field system. This expression is interesting and a little troubling. The troubling aspect of it is that the diagonal terms are actually infinite. If you take alpha equals to beta, you get q squared divided by 0 in the denominator, which obviously doesn't make any sense, although it's trying to tell you there's some kind of infinity. The infinity that appears here is actually the self-energy of the charged particles. There's quite a story in the history of quantum electrodynamics and in classical electrodynamics as well about the infinite self-energy of a charged particle. Let me explain the basic issue here. Is that if you have a charged particle, let's call it E instead of Q, then the electric field, of course, is given by the charge E divided by r squared multiplied times r hat. And thus the electric field energy is the integral over all space, d cubed x, of the electric field squared over 8 pi, over 8 pi squared. We're going to get an E squared coming out the front. And then the square of E is 1 over r to the 4th, like this. And if you do this integral, switch to spherical coordinates, so you can do the radial integral. You get an r squared dr you see for the radial part. That'll cancel out part of the r to the 4th, leaving you 1 over r squared. Well, the integral of 1 over r squared diverges. And it diverges because of what happens at the lower limit of r equals to 0. Let's replace this by, to take care of that, let's replace this by e squared over 8 pi. Let's make it an integral from a lower limit, let's call it r0 to infinity, r squared dr d omega, solve an angle, and then 1 over r to the 4th. And if you evaluate this, what you get is you get e squared divided by 2r to the 0. E squared over 2r to the 0. This is the energy in the electric field from the radius r0 out to infinity of a charged particle, assuming that the electric field of the charged particle obeys Coulomb's law, all the way down to r equals 0. This is the energy you get. And you can see that this energy diverges as r0 goes to 0. This is the singularity in the self-energy. It's called the self-energy of the charged particle, or the electron, self-energy of the electron. And it has to do with this divergence as R0 goes to 0. Now, in relativity theory, an energy, of course, corresponds to a mass. So dividing this energy by c squared ought to give us a mass. And this tells us then that if the electric field of, seems to tell us, if the electric field of an electron really does follow Coulomb's law all the way down to 0 radius, then the total energy in the electric field corresponds to a mass which itself is infinite. And therefore, how can we ever accelerate an electron if its mass is infinite? There's an old idea that goes way back before quantum mechanics. It's due to Lorentz and Abraham, which attempts to ascribe the mechanical mass of the electron to the energy in the field. In order to make that work, you have to impose a cutoff, R0, below which the usual Coulomb's law doesn't hold. We can ignore the factor of 2. It's really an order of magnitude estimate. But as an order of magnitude estimate, this R0 is the cutoff that's required to make this energy equal to mc squared, where m is the observed mass of the electron. And that radius is produced in this way, sometimes called the classical radius of the electron. Anyway, Abraham and Lorentz tried to develop classical theories for explaining the mass of the electron in terms of purely field energy based on these kinds of notions, and it never worked very well. And in fact, the ultimate resolution of the, such as it is, the ultimate resolution of this infinite mass problem only came about with the renormalization program of quantum electrodynamics, that is to say, through a quantum mechanical treatment and development of new ideas in quantum mechanics. So there's some very interesting history connected with that. In any case, that's something of a tangent for our present purposes, because in this potential energy that's emerging here for the interactions of the particles, if you compare this to what we do, the obvious thing we do in setting up a mechanical system of particles interacting by electrostatic forces, we would exclude the diagonal terms. We wouldn't even include them. They're obviously infinite, so they don't have any meaning anyway. We'd just throw them out. The normal procedure is to exclude the diagonal terms. So if you allow me, as an ad hoc procedure, to simply throw those diagonal terms away, then I'll replace this by the indication that alpha is not equal to beta, and by doing that, we then get the usual potential energy of interaction of the charged particles among themselves. All right. That, of course, you can question whether that's going to lead to trouble later on. And the answer is that yes, it does, but it won't do it for this course. But in the history of quantum electrodynamics, it became clear rather early in that history that there was a problem with this and that one had to take care of the self-energy and do it right. All right, in any case, for our course, we won't need to worry about that. So what this means then is that this electric field energy turns into the sum of harmonic oscillators plus the potential energy of the particles among themselves minus the diagonal terms which we're ignoring, infinite diagonal terms. And so now what about the kinetic energy? So here's the kinetic energy of the particles. There's nothing wrong with that. Here it is, it's just the kinetic energy, except for the fact that in the classical Hamiltonian description, Hamiltonians are supposed to be functions of momenta, not of velocities. And so what this suggests is that we need to express it in terms of the momenta. And what should the momenta be? Well, since we're guessing, let's guess that the momenta is what comes out of mechanics, classical mechanics of charged particles. It's the momenta is equal to the mass m times v plus q over c times the vector potential evaluated at the particle position. This is the usual formula, except I'm putting particle indices alpha on everything that depends on them. And we can then rewrite the kinetic energy in terms of momentum instead of velocities. So if we do all of this, then what do we get? We get a Hamiltonian. For the interacting system of the matter plus the field, and it looks like this. It's the sum over particles alpha. It's 1 over 2m alpha. The momentum P alpha minus Q over C, Q alpha over C, vector potential A evaluated at particle position R alpha, quantity squared. Let's make this bracket look better. We have then 1/2 the sum of alpha not equals to beta of Q alpha times Q beta divided by the Coulomb denominator R alpha minus R beta for the two particles. And then we have the sum on mode, sum on lambda of omega lambda over 2 times Q lambda squared plus Q lambda squared for the harmonic oscillators representing the transverse degrees of freedom of the electromagnetic field. And it's these transverse degrees of freedom, of course, which will represent light waves, and it's the exchange of energy between this final term and these other two terms which will govern the processes of emission and absorption of radiation. This could be done classically as well. In a minute we'll be doing quantum mechanics of this, but this could be done classically for a study of classical emission and absorption of radiation, now in the Hamiltonian formulation. So, we got the canonical variables, the Q's and the P's for the transverse components of the field. We got the Q's and the P's, we call them X's, we call them R's and P's here for the particles. And that covers both the field and the matter. And we got equations of motion, which are modified equations of motion right here in terms of the current. And if we want to do an honest job of this, since we've been guessing things, what we really need to do is to show that Hamilton's equations, which would be, R alpha dot is equal to partial of H with respect to P alpha, and P alpha dot is equal to minus partial of H with respect to R alpha, and then likewise the Q lambda dot is partial of H with respect to P lambda, and P lambda dot is equal to minus partial of H with respect to Q lambda. The classical Hamilton's equations, we would need to show that these are equivalent to Maxwell's equations for the field and the Newton-Lorentz laws for the particles. And I won't do that in lecture. I leave that as an exercise for you to do that. Okay. But then that then completes this and means that we have to do that. We have to do that check because we've been guessing. All right. Now, this completes almost everything that I want to say about the classical setup of the electromagnetic field. There's just one more comment that I want to make, which is that it is convenient to introduce what are sometimes called normal variables in the classical description. And the normal variables are harmonic oscillator variables. They look like this. This is called an A lambda is equal to Q lambda plus I P lambda. These are complex variables divided by the square root of 2H bar. And A lambda complex conjugate is equal to Q lambda minus I P lambda divided by the square root of 2H bar. These are classical variables, and even though I'm introducing H bars into them, this is still in the classical description. And if I do this and combine this with these C lambdas that you see over here, plugging this together, this is going to say that the C lambda is equal to the square root of 2 pi H bar C squared divided by omega times the A lambda, like that. So the normal variables are obviously classical analogs of creation and annihilation operators in quantum mechanics. And even in the classical description, they are convenient, in some ways more convenient than the Q's and the P's, which is partly why I'm introducing them, but also because in a minute we'll be doing the quantum problem. In any case, if we just do this and introduce yet another set of variables, these instead of the Q's and the P's, we can make this yet another coordinate transformation here if you want, to make this into the A lambdas and A lambda stars. Of course, this transformation that I've written out here not applied only to the field, it didn't apply to the matter. We have matter too, degrees of freedom as well. But in any case, if we do this, then the C's are given in terms of the A's by this formula. And allow me to do that, and allow me then to go and take these Fourier series, which we see here, and write the C's in terms of the A's. In fact, I think I want to do it in this very last expression here. Let me erase this here. That's right, this is A vector potential as a function of X is equal to what you're going to get is, you're going to get the square root of, in fact, let me write out the whole series. It's really just substituting this in, but here's what we get. we get the vector potential A as a function of x. It's the square root of 2 pi h bar c squared divided by the volume of the box. Sum on modes k, really sum of the modes of lambda is what it is. And we get 1 over the square root of omega lambda. That square root of omega lambda comes from the square root of omega you see right there. And then it's the A lambda times the polarization vector epsilon lambda times e to the k dot x plus complex conjugate. And likewise the A dt, which is proportional to the transverse electric field, is the same prefactor 2 pi h bar c squared over volume v, sum on lambda. And now we get an omega lambda upstairs because the time derivative brought down a factor of omega to get a minus pi a lambda epsilon lambda half e to the pi k dot x plus complex conjugate. And I'll leave these here for later reference because they will turn out to be useful later on. This is the expansion then of the vector potential and its time derivative and expressed in terms of the normal variables a and a star. Okay. Now, with just a few minutes left, those of you who might be thinking of questions might want to ask questions at this point and then send me an email because this is where we finish the classical description of this problem and turn to the quantum description. This completes the development of the canonical variables and canonical Hamiltonian description of the classical electromagnetic field interacting with non-relativistic matter. And we now want to quantize this. So if you have any questions, write them down and I'll answer in the next lecture. The next stage is to pass from the classical description to the quantum description. I'm going to do this initially for the free field only, having just spent quite a bit of effort, including the interaction of the matter. Let's drop the matter for now and just deal with the free field because there's enough to say about that alone. These expressions are still valid for the free field, but for the Hamiltonian, obviously we won't have the matter term here or the kinetic energy, either the kinetic energy or the potential energy of the matter. We just have the free field Hamiltonian, which is the sum of harmonic oscillators, as you see. So when we pass from a classical system to a quantum system, if the classical system has Q's and P's, which in the present context, speaking of the free field, are these variables I'm calling capital Q lambda and capital P lambda. When we pass over to a quantum system, these classical C-number variables become reinterpreted as operators. And they're required to satisfy certain commutation relations, which are a reflection of the Poisson bracket relation satisfied by the analogous classical variables. So just waving our hands to reinterpret the symbols now as operators, we require that these operators then satisfy what we call the Heisenberg-Born commutation relations. Is that they should be operators that satisfy the commutation relations Q lambda with P lambda prime commutator is equal to IH bar prime or delta lambda lambda prime. That means the Q and the P's commute with one another if the modes are distinct. You see the degrees of freedom of the electromagnetic field now are broken down into the degrees of freedom from the modes. Each mode is a separate degree of freedom. So the Q's and the P's commute with each other if the modes are different, i.e. if the degrees of freedom are different. That's just what you'd have in any system with multiple degrees of freedom. Likewise, any Q commutes with any other Q, and any P commutes with any other P. So the commutators of Q lambda prime, and Q lambda, P lambda prime are equal to 0. This then gives us a complete set of commutators for the Q's and the P's. And Hamiltonian, as I said, is just the free field part, so I'll write it down over here. It's just the sum of harmonic oscillators. It's the sum of harmonic oscillators lambda, omega lambda over 2 times Q lambda squared plus P lambda squared. Well, we recall what we did with the Dirac analysis of the harmonic oscillator. If we repeat that for this problem, the only difference being that we have an infinite number of one-dimensional harmonic oscillators, but for each one of them it's the same story. we introduce creation and annihilation operators. This would be A lambda would be Q lambda plus I P lambda divided by the square root of 2 H bar. In the creation operator A lambda dagger, this is an annihilation operator. The creation operator is Q lambda minus I P lambda over the square root of 2 H bar. Same formulas I wrote down earlier for the normal variables in the classical theory, except in the classical theory we had a star here for complex conjugate, and here it's a dagger for mission conjugate. Otherwise, the formulas are the same. However, the quantum variables don't compete with each other. Rather, there's a commutation relation in A lambda prime dagger. There's a conic result in lambda prime. These are standard harmonic oscillator commutation relations when you have multiple degrees of freedom. And I should say that all other commutators of A's and A daggers amongst themselves are equal to 0. These commutation relations are really just the same as these over here of Q's and P's, but just rewritten in terms of A's and A daggers. This is all standard for harmonic oscillators. Again, doing what's standard for a one-dimensional harmonic oscillator, doing it for all the modes, this Hamiltonian, when expressed in terms of the A's and A daggers by means of these formulas, gives us a Hamiltonian, which is the sum on lambda of H bar omega sub lambda times the quantity A lambda dagger A lambda plus a half, where the plus a half represents the 0-point energy of the oscillator. I'll come back to that in a minute. But again, this is just following what we did for one-dimensional mechanical oscillators. We get this expression for the Hamiltonian in terms of creation and annihilation operators. Okay, so this is the operator description now of the quantum Hamiltonian for the free electromagnetic field. There is, however, the question about what is the state space upon which these operators act. If we restrict attention to just a single mode, then we just have a single harmonic oscillator. And so the state space for that is just the same as the state space for a one-dimensional mechanical oscillator. Let's call it E sub lambda here like this, meaning the state space for mode lambda of the electromagnetic field. This is a space in which there's a convenient basis, which is the states n lambda like this, where n lambda is the quantum number of the oscillator. N lambda goes from 0 up to infinity, like this. That's for a single mode. And if you want the state space for the entire electromagnetic field, it's just simply the product or tensor product of the state space for each oscillator, one space for each oscillator. So it's a product over all modes, and this is actually a tensor product of the E sub lambdas like this. And this means that the basis in the entire space, the state space for the entire electromagnetic field, this is the free field I keep saying, it's the free field is all we're looking at for now. The basis is just the product of the basis vectors for each of the constituent spaces. So this is a collection of vectors that looks like this. Basically there's a string, you get an infinite string of harmonic oscillator quantum numbers, one for each mode. The modes are discrete because we're working in a box, so you can put them you can order them in a string if you want. Put them in some order like this, and then so for each mode there's an integer like this, and I'll represent the corresponding state vector, which is basically the tensor product of all these single n lambdas like this, with just putting a series of ellipses, dots here to indicate the missing elements. This represents an infinite string of integers, giving us the basis vectors. So this is the basis then in the entire state space for the electromagnetic field. This basis is called the occupation number basis, for reasons that I won't have time to explain tonight because I hear the bell, but that's what it's called. And I hate to get cut off right in the middle of something, but we will carry this forward and explore the basic properties of this quantum system in the next lecture.